We're often taught to be kind of wary of radiation, to think of it as this big, dangerous thing. But the truth is, radiation is literally a fundamental part of our universe. It's in the ground right under our feet, it's in the food we eat, and it's constantly raining down on us from space. So let's pull back the curtain on this invisible force and really get to know the energy that shapes our world.
So, let me just start by asking you a question. Are you being exposed to radiation right this second? The answer, and this might surprise you, is a definite yes. We all are, every single second of every single day. And by the end of this, you'll understand exactly what that means.
So here's what we're going to cover. First, we'll nail down what radiation actually is. Then we'll get into the two crucial types. This is super important. We'll meet the heavy hitters you really need to know about, find out where it's all hiding in our daily lives, and then we'll wrap up with 3 simple rules for staying safe.
Okay, first things first. That word radiation, it gets thrown around a lot, right? And usually it comes with this sense of mystery, maybe even a little bit of fear. So before we go any further, let's just strip away all the assumptions and put a clear, scientific definition on the table.
At its absolute core, radiation is just energy on the move. That's it. It's energy being released and traveling through space. Now, this energy can be in the form of waves, think about light or microwaves, or it can be actual tiny little particles shooting out of an atom. It's a really broad term, but that's the essential idea. Energy in motion.
All right, now this right here is probably the single most important idea in this entire explainer. You have to understand that not all radiation is created equal. There's a fundamental split, a dividing line that separates the everyday, totally harmless types from the ones we need to be smart about.
And this spectrum just illustrates that split perfectly. See over on the left, in the blue? That's your non-ionizing radiation. We're talking radio waves, microwaves, the visible light you're using to see me right now. But then, on the right side, in the red, you've got ionizing radiation, X-rays, gamma rays, and those little particles we talked about. And that line between them, it's all about energy.
So here's the absolute key. Ionizing radiation packs enough of a punch to physically knock an electron right out of its orbit around an atom. Non-ionizing radiation just doesn't. That's it. That is the critical difference. This act of knocking an electron off is called ionization, and it's what gives this type of radiation its power to actually change matter on a microscopic level.
And just to really lock this concept in, when radiation comes along and strips that electron away, the atom isn't neutral anymore. It's left with a positive charge, and we have a new name for it, an ion. This whole process is the reason this type of energy has both incredible benefits and, potential hazards. Okay, so let's zoom in on that high-energy ionizing team. There are really 3 main players, the heavy hitters, that you're going to hear about the most. And it helps to think of them as characters, because each one has its own distinct personality and its own special abilities. First up, we've got the alpha particle. Think of this one as the bruiser of the group. It's big, it's heavy, it's literally a helium nucleus. And because it's so big and charged, it dumps a ton of energy in a very short distance. It hits really hard, but it runs out of steam super fast. This means it's not a threat from outside your body, but if you were to inhale or swallow something that emits alpha particles, well, that's a different story.
And here's what that process, which we call alpha decay, actually looks like. You start with a big, unstable nucleus, something like uranium-238. And to try and get more stable, it just spits out an alpha particle. See that little cluster of 2 protons and 2 neutrons breaking away? And in doing that, it actually transforms itself into a totally new, slightly lighter element. In this case, thorium-234.
Next up, meet the beta particle. This is our speedster. It's basically just a high-speed electron that gets shot out of a nucleus. It's way smaller and lighter than an alpha particle, which means it can travel a lot farther and punch through more stuff. It's kind of like the middleweight champ, more penetrating than alpha, but not as much as our last contender.
So, where do these things even come from? Well, it's this fascinating little bit of nuclear alchemy. Inside an unstable atom, a neutron can suddenly decide to turn into a proton. Now, to keep everything in the universe balanced, it has to get rid of a negative charge, and poof, out shoots that super-fast electron that we call a beta particle.
And finally, we have the ghosts, gamma rays and X-rays. Now, unlike alpha and beta, these aren't particles at all. They're pure energy, super high-frequency photons. They have no mass, no charge, which lets them travel for really long distances and pass right through many types of materials. This is what makes them a significant external hazard.
This classic diagram just sums it all up perfectly. The big, clumsy alpha particle gets stopped by something as simple as a piece of paper, or even just the outer layer of your skin. The zippy little beta particle can get through the paper, no problem, but it's stopped by a thin sheet of aluminum. But the ghostly gamma rays, they go right through both, and you need thick, dense shielding like lead or concrete to really stop them.
So, we've met the heavy hitters, alpha, beta, and gamma. Now for the really big question. Where do we actually run into this stuff? The answer might surprise you. It's pretty much everywhere. We can basically divide all the sources into two main buckets. First, you've got the natural sources, the stuff that's been here since the Earth was formed. That's cosmic radiation beaming down from space and terrestrial radiation coming up from radioactive elements in the ground. And then you've got the man-made sources, which is everything from medical X-rays to certain consumer products.
And here's the real kicker. For the average person, the vast majority of your annual radiation dose comes from completely natural sources. As you can see on the left here, things like radon gas seeping from the soil and cosmic rays, they're the biggest contributors by far. Man-made sources, while we talk about them a lot, are generally a much smaller slice of the pie. And when we say radiation is in the ground, we mean it's literally in the materials we build our houses with. Just look at this table. Granite, clay bricks, concrete, they all have naturally occurring radioactive elements like uranium and potassium in them. That beautiful granite countertop someone might have in their kitchen, yep, it's emitting a tiny, completely harmless amount of radiation. It's a perfect example of just how baked in this energy is to our environment.
Now, when we look at that man-made slice of the pie, one category stands way, way above everything else, and it's probably not what you think. It's not nuclear power plants or fallout from old weapons tests. By far, the biggest source of man-made radiation exposure for the general public comes from medical procedures, like diagnostic X-rays and CT scans. And that's a perfect case of accepting a small, controlled risk for a much greater benefit. So that brings us to our final and maybe most practical section. Since we literally can't avoid radiation, how do we manage our exposure and keep ourselves safe? Well, it all boils down to three simple, super elegant, and incredibly effective principles.
These are the three golden rules you just have to remember. Time, distance, and shielding. It's really that simple. The less time you spend near a source, the lower your dose. The more distance you put between you and a source, the lower your dose. And finally, if you can't limit your time or get farther away, you put some shielding between you and the source. That's the whole playbook.
And that word appropriate shielding is so important. It ties directly back to our heavy hitters, right? You don't need a lead wall to stop an alpha particle. Your own skin does that just fine. But for those powerful gamma rays, you need something much more substantial. You just have to match the shield to the type of radiation you're dealing with.
So you see, radiation isn't some big, mysterious monster. It's a fundamental, unavoidable part of our universe. The key isn't to fear it, but to understand it and to respect it. It's the energy that's behind medical miracles and a source of power for our world, and we know how to manage it using three really simple principles. So I'll leave you with a final thought to take away. Now that you know all this, what's one source of radiation in your daily life? Like that granite countertop, or maybe even a smoke detector, that you'll look at with a whole new understanding. Thanks for watching.